so let's try it at number 33, A through D, and I'm going to do this problem 4 times, revolving it around 4 different axes. Let's start with revolving it first around the x-axis. So, as I said before, in order to get an idea of what's going on, I'm going to draw the reflection of this region over the axis. And I'm going to draw circles around corresponding parts. And I'm going to try to get an idea of what a typical washer might look like. Yeah, I draw the washers, and when I draw that washer, I'm very unsatisfied with this. Why? Well, because this part of the washer and this part of the washer are on the same curve. And that typically doesn't work out very well if they're on the same curve. The other thing is, if I did this, this washer has a thickness dx, but my problem isn't written in the form y equals. I would like everything to be the form, if I have a dx, I'd like everything to be the form of y equals something x. So those two things make me dissatisfied with the washer method for this problem. So I'm going to get rid of the washer. And so I'm going to replace it with a shell, a cylindrical shell. Now that shell, here's one side, there's the other, there's my typical cylinder. Now this cylinder, its thickness is grasped in the y orientation, and so volume is going to be thought of as a dy problem. The outside of that cylinder is a rectangle which has a width of 2 pi times its radius, and this radius is actually the height y. So there's the width of my rectangle. The height of my rectangle is this distance, which is the distance from x equals 0 to x equal that stuff. So that distance is 12 times y squared minus y cubed. So height of the, width of the rectangle that comes from unfolding the cylinder, height of that same rectangle that comes from unfolding the cylinder, a little bit of thickness to create a volume, and then the lowest value of y for the region that we're rotating is 0, and the highest value of y for the region that we're rotating is 1. And so there we have a very nasty integral statement that represents the volume of revolution. Let's clean this up. Let's take the 2 pi and the 2 and bring those out, and I get 4 pi on the outside. On the inside, if I distribute this y through both of those terms, I get y cubed minus y to the 4th dy. That looks quite a bit better. Yeah? Oh, it's a 12. So I figure that's really 24, isn't it? Is that right? I factor out a 2 and that 12. They combine to get a 24. Factor out the pi because it's also a constant. Is that better? Yeah? Okay. 24 pi, the antiderivative of x or y cubed is 1/4 y to the 4th. Antiderivative of y to the 4th is 1/5 y to the 5th, evaluated from 0 to 1, or 24 pi 1/4 minus 1/5 when I evaluate it at both 0 and 1 and 0. Common denominator there. I did that kind of quickly. Do you want me to go through the rest of that? I put a 1 and I get 1/4 minus 1/5. and I subtract it by putting 0 in, I get 0 minus 0. I've done so many of these that when I see a polynomial and I see evaluating at 0, I just write it off. It's probably not good practice because sometimes they actually do evaluate the things. All right, let's finish this off. 24 pi. Common denominator between 4 and 5 is 20. So this is 5/20 minus 4/20, which is equal to 24 pi times 1/20, which is 12, no, I can do better than that, which is 6/5 pi. Great, that's what they say it is too. Any questions there? Nope. Let's do the next one. Okay, this one's going to get revolved around the line y equal 1. This is going to be shells as well. Oh, it's used to use shells on all of them?
Yep.
Okay. So, not only is it what they want you to do, it's actually the best way to do it as well. So there's my typical shell. Here's my radius. And now the volume is going to be, again, from 0 to 1, because that's the values of y that cover the that region that I'm spinning around. 2 pi, because we're going to convert a radius into a circumference. And what is this radius? Well, if this is some typical y value, and this is the value 1, this radius is 1 minus y. So the radius is 1 minus y. Again, I'm going from the center of rotation, and I'm going down to the region that I'm rotating. Not up to here with its reflected image, but down to the original region. Now let's deal with that distance, which is still 12 times y squared minus y cubed, and dy for the thickness of the typical cylinder. This distance is going to be the cylinder gets unwrapped, but this distance is the circumference of that cylinder. Okay? This part is the radius of that cylinder. So here's the line around which I'm rotating. So this is the center of any of those cylinders, and I go down to the curve. Well, this point right there has the value 12 y squared y cubed, comma, y. The distance going vertically is going to go from this y equal 1 to this y equal y. So 1, the higher value, minus y, the lower value. All right. Let's factor out the 24 pi again. Integral from 0 to 1 of 1 minus y times y squared minus y cubed dy. I don't think I can use the substitution method here. Because if I do u equal y squared minus y cubed, I get a y squared. I don't see any y squared to cancel out with. So it looks like I'm going to have to expand that. 1 minus y times y squared minus y cubed. 1 times y squared is y squared. Y, negative y times y squared is negative y cubed. 1 minus y cubed is minus y cubed. And negative y times negative y cubed is plus y to the fourth. So it looks like we get y squared minus y 2y cubed plus y to the fourth. Darn algebra. Getting in the way of all this really nice calculus. But now, at least with it expanded, we can do the antiderivative relatively easily. Oh, forgot my limits of integration. Can't forget those. 1/3 y cubed minus 2 times 1/4 y to the fourth plus 1/5 y to the fifth as evaluated from 0 to 1. This 2 and that 4 cancel, and I get 24 pi times 1/3 minus 1/2 plus 1 plus 1/5. Common denominator of 30. Fractions, fractions. Okay, 10/30ths minus 15/30ths plus 3/30ths. No, 6/30ths, isn't it? Plus 6/30ths. So 16/30ths minus 15/30ths is 1/30th. So my ending answer is 24 pi over 30, which reduces to 6 goes into there 4 times, 6 goes into there 5 times. 4 pi over 5. Hey, 4 pi over 5 is the right answer. What? Only 2 more to do. Okay. All right, let's see how far. I may not get to the D, but I should be able to get C done in the remaining 9 minutes. Any questions there? Okay. Are you heartened to the fact that me, a pure mortal, can do this? And that you, given enough practice, can do it too? You know what? It's practice. It's really practice. All right. We're going to revolve this time around the line y equal 8/5. 8/5 is somewhere up here. My reflection is way up here. And here's my cylinder. Okay. And let's see if we can write this integral relatively easy. It's still going to go from 0 to 1. It's still 2 pi, but this time, what's our radius? I think it's going to be 8/5 minus y this time. High value minus the low value, because this point here is for some typical y value. And then back again to 12 times y squared minus y cubed. And again, the thickness of the cylinder is in the dy orientation. Y, or 24 pi. And now the expansion is going to be 8/5 y squared minus 8/5 minus another 1, be like 13/5 fifths y cubed, and then plus y to the fourth dy. 8 fifths, negative 8 fifths y cubed, and another negative 1 y cubed. Yep, 13 fifths. So now we've expanded out these two terms. All that other stuff got pulled out to the front. 24 pi times antiderivative here is going to be 8/15 y cubed. Here is going to be 13/20 y to the fourth and 1/5 y to the fifth as evaluated from 0 to 1. Ugly. Plug in all the ones, you got all the fractions left over. Plug in all the zeros, they all disappear. So what we're left with is 24 pi times 8/15. We lost a negative sign. We lost a negative sign right here and right there. Common denominator of 60? Yeah. We say begrudgingly. So it's 24 pi. 4 times 32 60ths. 3 is going to give us minus 39 60ths. And then multiply that by 12 plus 12 60ths. So 32 and 12 is 44. 44 minus 39 is 5. So we're going to end up with 24 pi times 5 60ths. 24 and 60 common factor is 6. 12. 12. So we've got 2 12s that we can take out of there. 5 12s that we can come out there. Boom, boom, those go away. It looks like we got 2 pi for our final answer. We might get the last one done. Let's give it a try. The last one is, by the way, more of the same. Okay, but this time we're down here at negative 2/5. That's our rotation, and so our reflected image is down here. And we draw a typical cylinder. And we're going to go from the axis of rotation back up to the original. And here we go. Volume is equal to the integral from 0 to 1. 2 pi, and now we need a descriptor of that radius, which is going to be y minus a minus 2/5. The high is now the y, the low is the axis of rotation, high minus low, y minus a minus 2/5. And then this, of course, becomes 12 y squared minus y cubed again, dy. Pull the 24 pi out again, 0 to 1. Correct that double negative, and we end up with y plus 2/5 times y squared minus y cubed dy. 24 pi. Integral, and then we got to do the expansion again. We get y cubed. I get y to the, we got a negative y to the fourth, and we got a positive. Why does this feel different? Oh, okay, because in the other ones we had the constant first. Hold on. Let me do this again. 2/5 times y squared. 2/5 y squared. Now, negative y, or positive y cubed, and then a negative 2/5 y cubed. So our net is a positive 3/5 y cubed, if I did that right. Okay, this one are these two. My next pair are going to be the ones that give me cubes. This one and that one. Positive y cubed, negative 2/5 y cubed, 3/5 positive left over. Okay, and then lastly is going to be my y to the 4th, which is going to be a negative y to the 4th, if I did that right. Y times negative y cubed, negative y to the 4th. 24 pi. 2 over 15 y cubed plus 3 over 20 y to the 4th minus 1/5 y to the 5th. Evaluated from 0 to 1. Common denominator here again is going to be 60. 24 pi 8/60 plus 9/60 minus 12/60. Okay, 17/60 minus 12/60 is 5/60 is 1/12. 24 pi over 12. 2 pi. Woo! Victory! All right. Practice, practice, practice.